Hi, we are Team Aurora working on the dual-use wideband microphone array system.
I'm the project manager, Hannah Louvier.
Hello, I'm Billy Flores.
Hello, I'm Jesus Hernandez.
Hi, I'm Daniel Lewis.
Hi, I'm Micah Snell.
Hi, and I'm Anthony Woods.
Our principal investigator is Dr. Richard Campo, and our NASA TSGC sponsor is Mr. George Salazar.
Our challenge was to design a dual-use wideband microphone array system.
As humans travel further into space, real-time communication with mission control on Earth will no longer be reliable.
Our system detects ultrasonic frequencies that are caused by pressure leaks and equipment failure and warns users of any hazardous conditions.
We also aim to provide a communication system for the crew members on board similar to a PA system.
As we combine these two systems into one, size, weight, and power are minimized, which is ideal with aerospace engineering.
We were tasked to create a design using MEMS microphones to transmit voice frequencies in the range of 200 Hz to 6 kHz, while simultaneously detecting ultrasonic frequencies greater than 20 kHz.
We'll use this signal generator to simulate an ultrasonic leak, and our system should activate a warning.
So let's talk about how we accomplished this.
This is our top-level block diagram. The dashed lines represent human speech, and the dotted lines represent the ultrasonic signals. Human speech and ultrasonic frequencies are simultaneously filtered to attenuate unwanted signals outside of their ranges. The system will pass human speech and emit a warning tone along with visually displaying the detection, direction, and intensity of an ultrasonic frequency. A challenge the team had was coming up with ways to test our system. So we started with two methods, with the leak simulator on the left and the frequency generator on the right. The leak simulator is designed to simulate air leaks at different pressures by adjusting the pressure regulator. And the frequency generator allows us to select ultrasonic frequencies and amplitudes for precise system testing. Unfortunately, the leak simulator predominantly produces audible leaks that are filtered by our system. The piezo speaker was mounted to a stand to prevent shorting. It is now our primary testing system.
The MEMS microphone array is 8 microphones and a one-dimensional circular array to show the sound localization capabilities of our system. The array is much larger than a flight-ready version would be to allow us to create and demonstrate the proof of concept. MEMS microphones are very small, and you could fit all 8 microphones on an array the size of a quarter. A Faraday cage throughout the assembly was made to protect the signal from the wires in the system behaving as antennas. Microphone 8's signal is used for both voice and ultrasonic functions.
This is the ultrasonic amplification and filtering system. The ultrasonic detection feature is made possible by two functions. First, the signals are received by the 8 microphone MEMS array. Each MEMS microphone will send a signal through its respective channel and then amplify to a detectable amplitude, which will set off the warning system. Second, the system filters all signals in each channel below the ultrasonic frequency range using 6th-order low-pass filters. The amplified and filtered signals through each channel are then output to the rectifier.
We're now at the ultrasonic rectification subsystem. The subsystem is made up of a half-wave rectifier that converts the alternating ultrasonic signal from Jesus' subsystem to a 0 to 1 volt varying DC voltage. The system can rectify different sinusoidal waves in the 20 kHz to 80 kHz range at varying amplitudes from 0 to 15 volts peak to peak, with an average voltage drop of 0.6 volts. A Zener diode clipping circuit was added to cap the output signal to 4.7 volts. This is to protect the warning subsystem Arduino analog input pins from exceeding its maximum rating of 5.5 volts.
We are now at the warning subsystem.
My subsystem receives input from the ultrasonic rectifiers and determines if an ultrasonic signal is present. When a source is detected, my subsystem outputs an auditory warning by sending a PWM signal with a frequency of 1 kHz to the audio output subsystem, and a visual warning by lighting an LED indicator. Both warnings scale based on the intensity of the signal. The auditory warning increases from 1 tone per second to 4, similar to a Geiger counter, and different colored LEDs are activated.
After receiving the signal from the warning subsystem, each microphone is updated on the GUI in real time. The visual display is comprised of a system status feature that notifies the user an ultrasonic leak was detected, a voice toggle switch to show if the voice communication feature is active, the signal intensity of all 8 microphones, and a sound localization feature that allows the system to detect and localize ultrasonic frequencies in a one-dimensional space. The localization feature of the GUI mimics the physical design of the array in the form of a circle. The signal intensity is represented by color, with red representing the highest intensity leak. This demonstration shows the functionality of the localization feature. As the microphone array is rotated, each microphone can read the ultrasonic signal and ultimately show which mic is experiencing the simulated frequency and the intensity of that signal.
The largest detection sensitivity of the system is around 24 kilohertz. At this frequency and of similar or greater magnitude, the detection range ranges from about 1 centimeter to 70 centimeters. Past this distance, the source leak would need to be of greater magnitude. To show the average detectable response for our system, the function generator is seen generating frequencies from 18.6 kilohertz to 44 kilohertz at the max range of 70 centimeters. The system can detect frequencies above this, though the source's magnitude would need to be significant.
The power supply subsystem uses one AC to DC converter that takes 120 volts AC from the environment and outputs plus or minus 15 volts. The voltage is then stepped down to give each subsystem its necessary voltage. The initial design used 2 converters, but to minimize the material and power used, only one supply was implemented. The applicable subsystems are receiving the appropriate amount of power while saving weight, which was a constraint for the project.
The voice channel receives input from microphone 8, then uses an amplifier with a 3.2 gain before cascading into a passive 6th order low pass filter with a cutoff frequency of 6 kilohertz. The communication toggle switch is a feature of this subsystem, which allows for the voice signal to proceed to the audio mixer while simultaneously passing a 5-volt signal to the Raspberry Pi to activate the voice active indication on the display.
This is the audio output subsystem. The audio output subsystem receives the warning tone and the filtered analog voice signal, sums the 2 signals, and outputs to an off-the-shelf power amp speaker. The audio output subsystem has a potentiometer which allows for volume adjustment of the voice signal over the warning tone.
To use the voice function of our system, the user activates the communication toggle switch. The communication toggle switch is a double pole, double throw switch, which passes the voice signal to the audio mixer as well as sends a voltage signal to the Raspberry Pi for the display. When the switch is activated, both the user interface and the red light on the LED will indicate that the microphone is live. The microphone used to pick up the sound is in mic 8 of our array and passes to the speaker. The volume knob can be turned from low to high. The analog mixer allows both voice and the warning tone to be heard through the system simultaneously. To silence the warning tone, hit the reset button. And to reset the system, press and hold the reset button for 3 seconds.
Some of the improvements we'd like to make with this system include advanced filtering. This would allow us to normalize the frequency response of the MEMS microphones in the upper range. Some of these upper range frequencies have a response beneath 0 dB, and honing in on those areas would allow us to better control the gain and increase the response in those areas. Another improvement we'd like to make is micronization of the entire system. So creating a custom PCB and using surface mount device would allow us to really minimize the space that we use and decrease overall weight. We'd also like to create better testing systems. It's kind of tricky to generate ultrasonic sounds and then also record them. So implementing some better systems to really verify that our system does what it's designed to do would be great. We'd also like to implement our system into a specific environment. This would really allow us to see where the system is strong and where it's weak. So improving on those areas would be very beneficial. We'd also like to implement a database that could log ultrasonic detections over time, and then using that recorded data, make improvements to software so that it's more dynamic in nature. And lastly, when you're floating around in space, you don't want to use a hardware switch to turn your microphone on and off. So we'd like to implement some voice control into the system.
Thank you so much to NASA TSGC for this opportunity to work on the project. Also, thank you to Dr. Richard Campo and Mr. George Salazar for all of their endless advice and support throughout this process. And also thank you to Texas State faculty for consulting us when we needed help. We will now take any questions that you might have.